Following on from the last video where the efficiencies of the conversion of the DC-DC in the solar whole system was looked at, I thought it would be interesting to see what our options were, the options we discussed last time, which would be a linear regulator and a buck converter. Having a 7805 lying around, and it's not really the most complicated circuit to build, which I'm going to get into shortly, put that together, and then I looked at the buck converter. I had a boost buck converter from Chinese supplier, again relatively cheap device, and decided to take some measurements and have a look at what we're getting at around a 1 amp load. So what I'm going to do is quickly touch on these two different converters, what the manufacturer said, and what we actually measured and calculated. An overview of the 7805 based upon, this is Texas Instruments data sheet. It's a 3-terminal regulator, so you can't really get much simpler than that. 1.5 amps output, which is great. We are looking at 1.1 amps, so that's not bad at all. Internal thermal overload protection, which means that basically it shouldn't explode if you short it off by mistake. Getting now onto a rough view of the specifications. There's a lot more specifications to be had if you really want to get interested in these things, but basically what it says is we can use 7 to 25 volts. It requires at least 2 volts above what it's putting out, which is the 5 volt. It could be used to do a variable voltage, but let's not get to those complications. Used in a straight simple configuration of putting 7 to 25 volts DC, get 5 volts DC out. Output current, as we mentioned before, 1.5 amps, and the operating junction temperature 125 degrees Celsius, which is, I guess, relatively high. One capacitor here, which was supposed to be 0.33. I couldn't find a 0.33, so this is a 1 microfarad, and then 0.1 microfarad capacitor. According to the schematic, again, this was supposed to be electrolytic, but I got the ceramic. 7805, it really is amazing just to put, three components and be able to get it in, out. Just gonna cut this on the device now and test it out. As mentioned previously, the board I got is a buck boost converter, so it has a LM2577 and a LM2596. The 2596 is the one that is used for the buck portion, so that's what we're going to concentrate on as opposed to the boost section. Quickly, it's an adjustable voltage output, 1.2 to 37 volts plus or minus 4%. TO263 package that was in that particular device. 3 amp maximum load, up to 40 volts input. 4 external components. I didn't fabricate this one, so that really didn't matter that much to me, except for cost wise, of course. 150 kilohertz switching frequency. Supposedly a high enough frequency. Let's see what goes on with that and how that helps us. Low power standby, that's always a good thing. Supposedly highly efficient, and we'll get into what the manufacturer says about efficiency in a little bit. And uses standard inductors. Most nearly anything could be found these days anyway. And thermal shutdown, current limit protection, so same thing. If we short it off, theoretically it should not explode. Getting to the manufacturer stated efficiency, again this is from Texas Instruments, just grabbing pieces of their data sheet. The efficiency is stated as 73% with our test voltage of 12 volts in, 3 volts out, so that's a fairly high variation range here. It's basically what, quarter the amp voltage, input voltage, so with a linear regulator that would have been 75% converted to heat, and a 3 amp load, so we'll see if we get 73%. And for completeness, I'm showing the adjustable output buck regulator. In all fairness to them, the one that is not adjustable, that's fixed, does have 4 components. This on the other hand has 7, and it clearly states on the bottom of that particular schematic that is copyright 2016 Texas Instruments. This is not mine, this is theirs off of their data sheet. So we're going to get some amount of heat dissipation here. I expect this to get very hot. I'm not going to go through the effort of trying to test that with a meter because, well,
hot to the touch to the point where it isn't feasible to hold it. That's hotter than you really want to be. So this is a no load situation. What I've done is taken off the negative lead. So 0 amps, 0 volts. Let me put it on. 12 volt power supply, computer power supply, 12 volts in, positive, negative, and looking across here now, 4.97 volts, 4.98 volts, thereabouts, so 5 volts. Let's put some load on it and let's see what kind of current we're getting. 1.13 amps, which is pretty good compared to a cell phone, and we're still keeping a reasonable 4.88 volts, and it is not that hot yet. Oh, too hot to touch. So this is getting too hot to touch in seconds. Now I could put a heatsink on that, and I probably do have to put a heatsink on that actually. Let's rephrase that. But in seconds I can't touch it. That's the amount of power dissipated. Ammeter today, I've decided to not put in the voltage on the output. We have already seen what it will be under load. So I've just connected now the ammeter to the input side to see what our input amperage was. We've gotten our output amperage, we've gotten our output voltage. Let's see what input amperage we're getting. And actually I should measure that voltage. That's 12 volts. That's a computer power supply. That doesn't drop under load. So that's 12 volts. It's pretty much a regulated supply. 1.12 amps, and this is on the input side I'm measuring, and let me see how hot it got. It's not that hot yet. Not that hot yet. Not too bad yet. Oh, almost impossible to touch already. The same arrangement with the buck boost board. Decided to keep this meter on. So just for the heck of it. Not that it matters because that wouldn't really change, and I've done the input side. So let's see what we're getting. Running through the negative and coming. And so the first thing is to see what the voltage would be without load, and then put the load on. 4.9 as it stands now. 1.17 voltage. So I can connect that. I'm not seeing that. As it stands now, there's a blue LED coming on. I'm actually seeing this pretty sure what that does. Again, no documentation. I'm just recheck on it and find out what that does. But anyway, going back, what we have is 5.02 volts, so practically 5 volts, 0 amps. We have not connected. Let's connect and let's see what we're getting. And there's an overcurrent, and it's limited to 0.8 amps. I'm going to have to adjust that, and we're down to 3.75 volts, which is terrible. Let me see if I can adjust that and make this thing work. Right, I've adjusted it. This thing is actually a current limited device. I'm not sure what the red means, but it's able to current limit. So I've managed to get to 4.94 volts, 1.13, which is relatively close, and this is actually getting fairly hot. Not too hot to touch, but reasonably warm, maybe at 50 or 60 degrees, and it's a couple seconds. It hasn't gone really bad. Let's see the input side. Let me see what power is being drawn, and then we can determine efficiencies. Decided to keep this meter on just for the heck of it. Not that it matters because that wouldn't really change, and I've done the input side. So let's see what we're getting, and we're getting 1.2 amps, 4.9 volts, 1.17 amps. So I'm not seeing an efficiency difference. I'm actually seeing this being basically just as bad as the 7805.
As predicted while making the measurements, the efficiencies turn out to be almost exactly the same. I mean, this is within the variation you get from those meters. We expected 73% at least, and that was with a greater voltage drop, and it turned out to be 39%, which turned out to be lower than the LM7805. As I said, that's within the variation. There's a National Semiconductor logo. It's part of National Semiconductor is part of Texas Instruments. It's Chinese made. Who knows? Maybe that's another device in there. Maybe it's a linear regulator in there, just being placed as a buck converter. The Chinese are amazing. They can do anything. So I do not want to cast any aspirations on Texas Instruments, but this is quite worrying and disappointing, and the regulation that I'm getting is highly inefficient.